let's try this again. So on yesterday's paper, first part was naming all the different parts. So you had name the circle. Again, we need to make sure that we're using proper notation when naming them. So they kind of already gave this away because it said up at the top, refer to circle P. This is circle P. Again, it's a circle with the center point. That's how we're naming it. Name a radius. So on here we have radius CP. And when we name a radius, it is a segment. So we name it as a segment. So segment CP is our radius. Again, you could reverse that. Now it said name a radius. It didn't say name all the radii like it did on the other one. So if you listed more than one, that's fine. You could have also put AP or PB also work. But again, it only asked for one, so you didn't have to have all three. Name a chord. Again, only asked for one. So there are two chords in this diagram. DE is a chord, or you could have also done AE. Name a diameter. Now there's only one diameter, so it had to be AE. Again, every single one of those pieces on 2, 3, and 4 were segments. So we use our segment notation when we're talking about them. So number 4, that was segment AE was our, sorry, A. I did the wrong letter there. A, B. That's the one that goes all the way across. My bad. All right. Number 5, name a radius not drawn as part of a diameter. So the only one of the radii that's not part of the diameter would be CP. All right, so segment CP. Number 6, suppose the diameter of the circle is 16 centimeters. Find the radius. Well, if the diameter is 16, how do we find the radius? Divide it in half. So if we take 16 and divide by 2, our radius is 8. Again, since they gave us units, we should always write the units. Now they said if PC is 11, so PC is our radius. Find AB. AB is a diameter. So if the radius was 11, then the diameter is going to be what? If the radius is 11, it's 2. So 11 times 2 is 22. This was in inches this time. For the next one down there, we did this one in class yesterday, but just to recap, we had 2 different circles there overlapping. It said that for circle F, we had a radius of 5 units. So this piece was 5. BG then was a radius for circle G, which was a length of, oh no, sorry. That was the diameter, my bad. So wait, that's not what I remember from yesterday. This whole thing was 5. So this little piece is 2.5. The diameter is 6. So the radius here is 3. So the difference between these 2 little pieces makes BF 0.5, and that's the answer for the first part. Then they wanted AB. Well, if this entire length from F to A is 2.5, we had to subtract off the 0.5, and it gave us just 2. So that was 0.5, and this piece was 2. All right. Number 10. Actually, all of these, 10 through 13, kind of doing the same thing. They gave us a circumference. They asked us for the diameter and the radius. Again, we have our formula for circumference is C equals pi times diameter. If they gave us a circumference, in order to get diameter by itself, we'd have to divide off pi. So in each case here, we're going to do the circumference, divide by pi, and get our diameter. Once we know the diameter, we can split that in half to get our radius. So we have 36. If we plug that in, 36 divided by pi. And this is giving us our diameter. Calculator. It's not popping up. Yep. All right. For some reason, I can't show my calculator right now. It's not working. But for our diameter on that one, 11.46 would be our answer for the diameter. So that was correct. Thank you. And that was in meters. And then for our radius, split that in half. So divide that in half. Our radius is going to be 5.73, again, in meters. On number 11, they have our circumference is 17.2. Again, to get the diameter, we'll take that and divide it by pi. You should get roughly 5.47 feet. The radius would be half of that, which would be 2.74 feet. Now, notice, is this half the number that I wrote up there? So the radius that I just wrote, was that half of the first number that I just had? No. But this is half of, like if I doubled this, I would have had 5.48, right? Again, whatever's in your calculator, once you got this, make sure you divide that in half, not this answer, because you get a different answer sometimes when rounding, especially when it comes to the radius there, since there's more decimals still when you got that answer for your diameter. So make sure you hold on to those extra decimals, divide it in half, because it will change your answer. Yeah, you don't want to round until the end of a problem. All right, number 12, we had, again, same idea. So just writing these two answers out, the diameter on this one was 25.88 centimeters. The radius was 12.94 centimeters. On 13, we had the diameter was 1.59 yards, and the radius was 0.8 yards. Again, that's another one where if you, well, no, that one probably would have rounded the same, but all right, questions on those? All right, I see some writing, so I'm going to pause for a minute. Let me clear that and move this up. So 2 at the bottom. Can't quite fit those on the screen before. So zoom in. So find the exact circumference of each circle. Again, we're going to have to use our circumference formula. Either circumference equals pi times diameter, or circumference equals 2 pi r. On this one, and we have a square. The square is then split with a diagonal. So these are actually two 45, 90 right triangles. If the side lengths are both 3, then the hypotenuse is 3 radical 2. So when we plug it into our formula, we're going to have circumference equals our diameter, which was 3 square root of 2 times pi. That is already in terms of pi. That is an exact value. You don't have to do anything else. That is our answer. Number 15. All right, we have 8. We have 15. This is a Pythagorean theorem problem. So this 8 was on this side. So just want to make sure we understand where that was. So if we put them in the same triangle, those are my 2 legs. I need my hypotenuse. C squared equals 8 squared plus 15 squared. C squared equals 64 plus 225. And that together we get 289. Square root 289. And C is, let's see. Square root of 289. So one of our perfect squares. Comes out to a whole number. 17. That was actually one of our triples. So again, if you knew that triple, that's not one of the 2 that I said was the most important though. So I went ahead and did my Pythagorean theorem. But again, it is a triple. So if you recognize it early, we could have just said, all right, that's 8, 15, 17 had to be that third side, and we would have had to done that work. Now, we know that this piece is 17. Our answer though, we're looking for circumference. So we have the diameter. So circumference equals the diameter times pi. So 17 pi, and this is in feet. Sorry. Questions there. All right. That was that whole first page. The second page, the problems are almost identical. So I'm going to write out all the answers this time first, and then if you have questions, I will come back and do any of the ones that you want me to do. So let me save that and clear it. I need to go past that. Out just a hair. All right. So on this one, same thing, naming the parts. So this first one was circle L. Radius, you had a couple different radii that you could list, either LR, LT, or LW. Any of those would work. It's a name accord, so you could use either RT, RS, or ST. Again, you didn't have to use all of them. For number 4, what was the diameter? It was RT. Name a radius not drawn as part of the diameter, so that was LW. Number 6, suppose the radius of a circle is 3.5 yards. Find the diameter. That's going to be 7 yards because we doubled it, right? Times 2. Number 7, find LW. That's going to be 9.5 meters. They gave us the diameter, so we divided by 2. That gave us the length of the radius. Number 8, we had a very similar question as the last one. So you had to first label your different parts. You're given the diameters. You're also given QR. You had to then figure out what the missing pieces were. So LQ was 6 and RM was 2.5. Do you want me to go through that one? All right. So on the diagram, we have 20 for our diameter of this one, right? So each of these, this piece and this whole thing together, is 10. Let's see, the other one for the smaller circle, we had 13. So the entire thing's 13, which means that this piece is 6.5. Same thing with length here is 6.5. They also told us that QR is 4. So it gave me that length too. The only piece that, or the piece that we needed to find first was LQ. LQ is this piece. So we know this whole thing's 10 from L to R. You know this piece is 4. So we can subtract the difference. 10 minus 4, it leaves us with 6 for LQ. And then they wanted to know the length of RM. Well, if this is 6.5 from Q to M, subtract 4, and we have 2.5. Yeah. Questions there? This up. So now on number 10, it says find the diameter and radius of the circle given the circumference. So same idea that we had on the last one. Really, all we have to do is divide by pi. That's going to give us the diameter. So 21.2 divided by pi gave us a diameter of 6.75 feet. Divide that in half. Our radius was 3.37 feet. On the other one, same idea, divide by pi first. Our diameter was 1.88 meters. Our radius, and half of that would be 0.94 or 0.94 meters. On 12 and 13, we had another Pythagorean triple. Again, if you didn't recognize the triple, you could plug it into Pythagorean theorem again. But this is a 724. Anybody know the other side? 7.4. It's in the 20s. Anybody know it? 25. So this is another triple. Again, if you don't know that triple, then do Pythagorean theorem. Again, that would be c squared equals 7 squared plus 24 squared. That would give us c squared equals 49 plus 396? No, that's not, that's too high. No. 576. Oh, yeah, I'm way off. I was thinking 19. 576. All right. Add 49 to that. That gives you 625. 625 is a perfect square. That is 25 squared. So 25 is our answer. Again, once you knew that side, whether you did it with our Pythagorean triple or our Pythagorean theorem, then you plugged it in to our equation for circumference. So circumference, we're just taking the diameter, multiplied by pi, and that's it. That's our answer. On 13. Now, this one, I don't think this is any of our properties. I don't think this one works out to a whole number. You'd have to do Pythagorean theorem on this one. So c squared equals 40 squared plus 42 squared. 40 squared is 1600. 42 squared, don't know that one off the top of my head. That's 1764. So add those two together. It gives us 3364. And then square root that, and we get 58. Apparently that one is a triple. I don't recognize that. Could we have simplified those? Let's see. Yes, those are all divisible by 2. So 20, 21, 29. I don't know that one from memory, but that one must be a triple since we had all whole numbers. Again, I don't expect you guys to know all the triples. The couple at the beginning, those are the only ones that I said you really need to memorize, because you can always do Pythagorean theorem to make it work. All right. Once we had C though, so plug it in. Our circumference is equal to 58 pi in miles. All right, on 14, it said Herman purchased a sundial to use as the centerpiece for a garden. The diameter of the sundial is 9.5 inches. Find the radius of the sundial. Well, what do we have to do? Take that 9.5, divide it in half, and what do we get? 4.75. That was in inches, so this is in inches. Find the circumference of the sundial to the nearest hundredth. So we have both the diameter and we have the radius. Doesn't matter which one you use. I prefer using the diameter if we have it, since it's just that times pi. So we have circumference equals 9.5 times pi. This one did say round to the nearest hundredth, so we do need to plug this in. So 9.5 times pi. So we get 29.8. And I'm going to put the rest of the decimal here for just a second. We're rounding off to the hundredths place. So you're right to say 29.85 for our final answer. And this was in inches. So our circumference is also in inches. Now, since that's a bigger value than some of the earlier numbers that we had got, depending on what you used for pi, would have changed your answer. So if you used pi on the calculator, you got 29.85. If you use 3.14, you've only got 29.83. So again, depending on what you used for pi does make a difference in your final answer here. I suggest that if they don't tell you what to use for pi, use pi on the calculator. So it's a little more accurate. If it doesn't, if it does tell you what to use, so if it says use 3.14 for pi, then use whatever it's asking. All right, let me save that. Let's see, we're in here. 30. I have a couple different things printed off. Let me see where I want to go next. Do I want to do this next? Yeah, you know what? Oh, just use this. I'm not going to give you an assignment this weekend, but I do want to take a few other notes today. There are 2 charts that I'm going to give you during this chapter so that everything's kind of in one place to help you study. Again, there's a lot in this section, like I said. All right. So on here now, some of these we already did, all right, but I'm going to recap these real fast, just so that we have everything, like I said, in one place. So on the first one, the main idea there, again, you can pull some of these things directly from the worksheet that we just did, but again, it's nice to have everything in one spot to study from. So from yesterday's worksheet, again, we had some basic definitions that you should know. For the first one, this is just a circle. All right. For the details on this one, again, what is a circle? It is the set of all points a given distance from the center. All right. The other one there, the next one down, that is showing us the actual center point. So on here, center point. Once again, the point at the center of the circle. Then we have on the next one, what's in that diagram? That is our what? That's our radius, right? So then what is the radius? Okay, so we can say a couple different things about the radius. By definition, it's going to be the length, or it's going to be a segment that goes from the center point to the side of the circle. So the segment, or I should say a segment, maybe a segment that has endpoints on the center and on the circle. Also, you should know that for radius, the plural form of radius is what? Radii. So that here as well. I always think it's funny that when you are talking about plural and ends in us, which us is usually a plural word, then you get rid of us and you put I, and now it's plural. Sometimes I don't think English makes any sense. Radius, radii. All right, so now over here on that diagram, let me go ahead and label that as well. So again, this piece, that is our radius. And again, we have our two endpoints. We had one endpoint on the center. We have one endpoint on the circle. All right, moving right along. This one, what was that piece again? That was our chord. Good. And our chord is defined as a segment that is what? What is a chord? A segment in a circle with both endpoints on the circle. Yeah, try to make these definitions short enough to fit in there. The last one, we know what that is. That's our diameter. And again, a diameter, by definition, it is a chord. So that's what I'm going to use as our definition here. A chord that passes through the center of the circle. Other things to note there, it is the longest chord in a circle. The whole thing, the diameter. All right, so those are ones that we saw on the first sheet already. On the back, now we're talking about angles and arcs. All right, so let me save that. So this is a little bit different now. Now I'm not going to give you the come on, change. There it goes. I'm not going to give you the assignment that goes along with this just yet. I'll wait till Monday to do that. But let's talk about all these different pieces. So first, I'm going to name what each of these figures is showing us. So on the first one, that is a central angle. That is a central angle. The second one, now, there are 3 arcs here. Right? The first one is what we refer to as a minor arc. The next one is going to be a major arc. Now, the next one, you may know the name of that one. Anybody know the name of that one? No. So that's exactly half a circle. What do we call half a circle? So that's with an S. No. Half of a circle. Semicircle. Yep. And then this last one, we're actually going to use for something. We did what was called segment addition, and we did what we called angle addition before. This one I'm using to talk about arc addition. So what are each of these things? Central angle, kind of think that one's almost self-explanatory. What is a central angle? What do you think? Central angle. So on that one, we are talking about the angle itself there. So we're looking at this angle. I'll highlight it in blue for you. So this angle that goes from here, there. What is that? Okay, now it doesn't have to be a right angle. So the one that I have drawn here is a right angle. Now, if I look at these other diagrams, these other angles that I have are also central angles. All right. So it's going on the center point. So the actual definition is just a angle with the vertex on the center point. And that's it. That's a central angle. So an angle in a circle with the vertex on the center. Let me make it smaller and see if I have enough room to the right point. Now, one thing that's important to note here, whenever we're looking at a central angle, the angle and the arc that's being intercepted by the central angle will always have the same measure. So I'm just going to write that off to the side here. And if you want to just jot it somewhere off to the side, that's fine too. But the central angle and the arc of the circle that it intersects. Actually, they like to use a different word here instead of intersects. Usually they say that the arcs, the angles are intercepting the arcs. That it intercepts to be correct tense. The central angle and the arc of the circle that it intercepts have the same measure. So on this diagram, I'm going to go ahead and label this. Since you said that this looked like a 90-degree angle, I think you're right. I'm going to go ahead and call that 90 degrees. This arc out here is also 90 degrees. All right, the next one, minor arc. So what do you think a minor arc is? So we had a minor, a major, and a semicircle. What do you think defines a minor arc? You want to take a guess? How about this? Let's move down to semicircle first. What do you think defines a semicircle? It's half of a circle. Well, what is a full circle? How many degrees are in a full circle? 360. Good. So a semicircle is, it's an arc. An arc that is exactly 180 degrees. Have a degree mark on that. So now that we have that definition, let's go back to minor arc. What do you think a minor arc is? Less than 90. So like, look at the one that's there. Does that one look less than 90? No, but it's less than what? Less than 180. So an arc with a measure between 0 degrees and 180 degrees. Oops. Now, I'm also going to go ahead and label this diagram over here. Here's arc AB. All right. So when naming an arc, very similar to naming an angle, I'm going to use, or really more, even more similar to naming a segment, I'm going to use these two endpoints of this arc. And I would call this arc AB. Now notice, I use two letters, same as with my segment, right? I use the two endpoints, and that's how we write an arc. Now, the other one, so that's an arc between 0 and 180. What do you think a major arc is? Higher than 180, less than 360. An arc with a measure between 180 and 360. So this one being a major arc, I'm going to put those 2 points on, but I'm going to put a third point over here. Let's call this D, E, and F. When I name this arc, I have to use all 3 of those points. I have to use the 2 endpoints, and a point between them. Because if it has just said arc DF, then I'd be talking about the minor arc that was between points D and F. So I have to show the direction is going to the bigger side of the circle when I do a major arc. All right. And then arc addition. Are we really done already? Yeah, I guess 38. All right, so arc addition, the measure of the arc formed by two adjacent arcs is the sum of the measures of the two arcs. I'll post that one, but it's basically the same as our angle addition postulate or segment addition postulate. So the measure of an arc formed by two adjacent measure of an arc from which measure of an arc formed by two adjacent arcs is the sum of the paper from yesterday. What's this guy here? But it is the same as 2 days ago as well. All right. So if those two, I think it goes differently. So if this was 40, what did I say it first time? 45, and this was 50, then this entire arc is going to be 95 because this arc is the same as its in central angle. This arc is the same as its central angle. So together, it's those two combined, which is 95.